Morning, everyone. Today, I'm going to talk about XGBoost, a scalable tree boosting system. This is a work in collaboration with my advisor, Carlos Gastrin, in University of Washington. As we all know that machine learning and data mining are impacting our daily lives in all the aspects. It helps us to improve our web browsing experience. It improves our lives in various aspects in terms of giving correct credit fraud prediction, handling malwares, and help us to advance science, I mean real science, by using all those algorithms to detect high-energy physics events and discover new physics. This is an incomplete laundry list that you don't need to gloss over them, but if you catch some of the things, some of the keywords that you might be interested in, this might be some good reason that you want to come to this talk. Okay. And as we can find, there are a lot of applications for machine learning and data mining nowadays. It's good to ask that what are the good methods for these problems? Well, deep learning, which is a recent hype, is definitely one of them. And if you're interested, we have an MXNet hands-on tutorial, shameless plug, on this afternoon. But I wouldn't be talking about deep learning today. I'm going to talk about another method that is highly effective and have been around for more than 10 years. This is called tree boosting method, invented originally by Friedman in the 1990s. And in general, the tree boosting method tries to build ensembles of regression trees to make a strong predictor about behaviors of user or the quantities that you are interested in. It's so powerful in a sense that this specific type of method is used to win more than half of the data science and machine learning challenges in the past year. And today, I'm going to talk about a system that's actually used by all these winning solutions. And that is XGBoost. I want to emphasize that I want to talk about the aspect of systems as well as algorithms in these following four aspects. And it is a combination of these all four aspects that makes the system great for everyone. When everybody talks about machine learning, the first thing that you want to think about is how accurate can I make my prediction given the existing data. By accurate, it not only means that it can fit your training data well, it also means that you want to generalize well to the unseen data set. On that aspect, when we train a tree ensembles, we can formally write down a supervised learning objective as we all do for all the other kind of supervised learning. It usually consists of one part, which is a training loss that measures how good you're doing on the training data. What I'm going to emphasize more is a bit new piece that we bring to the tree ensemble training. It's the additional explicit regularization term that we place on each of the individual trees, so that we are penalizing the complexity of a tree by the number of leaves, as well as the L2 norm of each of leaves. So this explicit regularization can be combined with the implicit regularization that you might heard for those tree boosting algorithms like step size and limiting the maximum number of depth trees to make the tree boosting training more conservative and less easy to overfit. If I haven't yet convinced you why regularization is important, I hope to use this following intuitive example to show why it is the case. Assume that I want to fit a single regression tree on a one variable, that is the data point here. There are several ways that we can fit it, and since we are dividing on a single variable, actually we are fitting step functions. This is the first type of step function that you can fit. You can find it fits the data point well, but have too many splitting points. This is the second type of step function that can fit, which is simple, but does not fit the data well. Finally, by combination of the simplicity and the predictivity, we can get a good model that hopefully you agree with your own mind. And this basically illustrates why we need to trade regularization with the predictive power of the model. OK, now we have explained how a bit of source that can get more accurate. Let's talk about another point. Everybody wants to train their machine learning model faster, so that I can finish my experiment faster and get more productivity in writing papers. There are two aspects here. The first aspect is being able to handle sparse data well, in a sense that if you look at your training data in all these cases, in almost all the cases, the data is not perfectly dense matrices. There can be missing values, and there can be other sources of sparsity, such as feature engineering, etc. what we do is we introduce a unified data structure to handle the missing values and sparse data by introducing a default direction when the data is missing, so that users no longer have to manually impute their missing values anymore, and it automatically handles it for you. Now we are talking about making the training step faster, and actually the most time-consuming part of doing tree boosting is finding a splitting point, in a sense that every time we are trying to expand a new split given the existing tree. To evaluate how good a splitting point is, we have this formula that I haven't been derived, and you don't need to understand what it is. But the key message here is that it is sufficient to evaluate some statistics on each of our branches to see how good that splitting point is. For sparse data, we want to have a specific algorithm to do a sparse-aware splitting finding, in a sense that we will sort the data in sorted order and enumerate over all these possible splitting points one by one, but we will only stop at the unobserved values. And we'll use the subtraction to get the statistics of the unobserved values. This algorithm will reduce the complexity from number of entries in the full matrices to the number of entries that you're seeing in the entire matrices. And this makes a huge difference if your data is really sparse. For example, here's an example on a reinsurance data set that we run. Here's the training speed of the basic algorithm, and here's the training speed of the sparse-aware algorithm. You will find that there's the 50 times gap between these two algorithms. OK, besides this algorithmic improvement, we also introduced another system improvement to the algorithm. The idea is that we will pre-process the data set to a sorted order, so that when we are scanning through the feature values, we can parallel scan through them over this sorted data structure. This allows us to reduce the time complexity of the splitting finding or histogram aggregation from log linear time to linear time of each of the instance. And that additional log linear time saving, that additional log saving is also significant. However, this type of column-based structure also brings problems, in a sense that now we have an indirect link to each of the gradient statistics. If the gradient statistics do not fit into a cache line, there can be cache miss problems. And we will need to use some techniques like cache-aware prefetching and reducing the block size in approximate algorithm to solve this problem. Here's an example of comparing cache-aware algorithm and cache-unaware algorithm on a 1 million data points data set. You can find that there isn't much of a difference. But this is actually because the data size is too small. If you change it to 10 million, you can find that there's the 2 times gap between the cache-aware algorithm and the cache-unaware algorithm. And by bringing cache-aware algorithm into account, we can really make the speed fast in both small data setting as well as big data setting. OK, being fast is great, but being able to scale is even better, in a sense that we're at KDD and we want to talk about big data. The challenge when you want to bring the algorithm to big data is that you can no longer store the entire data set on a single machine's memory. So you cannot sort the data over the entire data set anymore. In order to solve this problem, we want to introduce the approximate algorithm that contains the following step. First, you will get a data set. Actually, conceptually they are the entire data set, but they are actually distributed across machines. First, we'll propose some candidate splitting points to choose from. Then, distributedly, we'll aggregate the histogram of each of the data points into the bucket. Then we will only enumerate over the candidate splitting point to find the best candidate for the next split. The key problem here is that how we can find good candidate splitting points given the existing data set. The idea is that we want to find candidate splitting points such that they equally divide the feature space so that they are equally spread out. And if you are from database community, you can find, you'll notice that this corresponds to a traditional problem called quantile founding or quantile sketching problem. And this problem is actually a non-trivial because you can no longer simply sort the data set and pick up the quantiles. There's an existing solution from Sigmund in 2001 called GK summary that solves the quantile sketching problem when data points do not have weights and they are equally weighted to each other. In our problem, we need to solve an even harder problem, in a sense that each of the data points can be weighted because of the gradient boosting process. And we need a new sketching algorithm to find distributed quantiles for weighted data. I do not have time to talk about this algorithm, but you can find the details in the paper. Now we have talked about approximate algorithms and how we can use them to handle big data. Let's talk about how we can move the system to handle this big data well. The first setting that we're targeting at is an out-of-cost setting, in a sense that not all your data fit into a memory, but you have abundant hard disk to store the data, and you can use this hard disk as a backup for your training. The procedure works as follows. We store blocks of each of the data in multiple SSD or hard disks. We have an independent thread to prefetch those individual blocks into memory. And we will have another thread that runs the computation. Actually, simply doing this is not enough, in a sense that because the disk throughput is much smaller than the memory throughput, and we are going to bottleneck by disk if we do this naively. What we need to do is we want to apply more system optimizations to compress each of the blocks so that the disk bottleneck is reduced. Particularly, we'll use 16-bit index on the feature blocks index, and we'll compress the floating point value in solid order so that the compression ratio can be maximally achieved. We also further shard the data set into multiple disks so that we can load from multiple disks concurrently and even get a better throughput. OK, we have talked about out-core computations, and let's bring it to practice. This is an example on 1.7 billion as click-through data set from Creative. This translates to around 1 terabytes of data if you store that in text format, and 300 gigabytes of data if you store that compressed in memory. The x-axis is the different number of subset of training set, and the y-axis is the time per iteration cost, so lower is better. This is a log-log plot. This is a basic algorithm that only handles 1/10 of the entire training set and no longer proceed further because it runs out of resources. By adding block compression, we can get to around half of the data set. By adding all the optimizations, we can train the entire 1.7 billion data set on a single machine. And that's a typical EC2 machine that you can get from any of the cloud services. And we are really pressuring our system in a sense that this is a real out-of-core setting, and the system is really run out of file cache and relies on the disk throughput to do the out-of-core computing. This is great in a sense that we can process a lot of data on a single machine. But why not stop at a single machine? Usually, people talk about distributed computing. In here, in XGBoost, what we can do is that we can distribute the data set across multiple machines, use the same column block on each of the machines to make the histogram aggregation and quantile founding faster. And the time complexity benefit from the new data structure we introduced, in a sense that we can use a merge sort style to find the histograms and directly founding the quantiles before merging them. So we can bring all this together, distributed computing, out-of-core computing, and all those optimization together, and test it out on a 32-machine EC2 environment. This is the same data set, 1.7 billion, with 32 machines. However, each of the machine's resources is smaller than the beefy machine I used for the out-of-core computation. We compare end-to-end cost for 10 iterations. Again, lower is better. And we compare against 2 existing open source systems that does gradient tree boosting. Here's the result for Spark MLlib that runs all of the resources around half of the data set size. And here's the result for H2O, which is another gradient tree boosting system. By using XGBoost, the takeaway message is that we can be faster. Since notice that this is a log-log plot, so the gap actually indicates a lot of things. More importantly, we can scale further to fully utilize the 1.7 billion examples on these 32 machines. If you come to my poster yesterday, you must notice that I also have another plot that allows us to scale, instead of scale up, to scale down, to use as little as 4 machines to train this 1.7 billion data set using XGBoost. The key takeaway here is that we really want to push the limit of each of the machines to use fewer resources as possible so that you can scale to terabytes of data, tens of terabytes data, or even further, using as little resources as possible. OK. So you might say, this is great. How can I apply that to my own work? And that is the problem many people ask when they want to use some new learning system. And this is actually a very hard problem in a sense that there are a lot of subtleties on all these platforms, and it's very hard to migrate from one platform to another. If you look at traditional machine learning platforms, it looks like this. We have several types of data processing platforms and machine learning platforms, such as Apache Flink, Spark. Each of platforms have their own implementation of machine learning packages that are tied to the platform. XGBoost is different. We have a unified abstraction that can run across all these platforms so that it's no longer restricted to a single platform, but can be applied to any of the platforms that you use in your production. To put it into details, you can use XGBoost in any of your language. You can pick your favorite. All of these languages are backed by a unified backend that's fully optimized with all the aspects that I talk about in this talk. You can also use it in any of the distributed platforms. You might notice, for example, Apache Yarn. And you can use it on top of the data flow programs, such as Apache Flink and Apache Spark. I want to emphasize again that the system is platform agnostic, in a sense that, for example, if you want to migrate your solution from an existing platform to a new cloud platform that may not have machine learning package available, this optimized package is already there for you without any of the cost. OK. I've talked about these 4 points, and now I want to recap and summarize. It takes a regularized tree boosting objective to make the training more accurate. By using sparse-aware and cache-aware data structure, we can make the training faster on single machine on both small and big data sets. We can use distributed and out-of computing to make XGBoost scale to large data sets. And finally, we can use a platform-agnostic abstraction to make the solution portable to any of the platforms that you might want to run. It's a combination of all these 4 elements together that makes a system that is already widely used by data scientists, by Kaggle competition winners, by industrial practitioners. And hopefully, in this talk, I can convince you that you might want to use this system as well in some of your work. That's the end of my talk. Thank you very much.
Thank you. Very amazing talk. So one of my questions is that how well are you performing on sparse features on your tree? Because like in my experience, that sometimes sparse features, sparse data set doesn't the boosting tree doesn't perform very well on sparse features. The second question is that another problem in my own experience that sometimes predicting the tree is, if the trees are large, so on the inference time, it's very time consuming. And it's often the bottleneck of system instead of the training of the tree. So do you have some answer for them?
So the first question is that how does it perform on sparse data?
Yes.
First of all, XGBoost is well optimized for sparse data in terms of training complexity, in a sense that it's guaranteed to be fast. However, if you talk about accuracy, actually tree boosting methods are not very optimized for heavily sparse data set. So that's where you might want to do some feature engineering to further improve your performance. The second question is on inference time. That is indeed a big problem here. Actually, we have some ongoing work on improving the inference time as well, and that's a separate future work that I think is exciting. Yeah.
Thank you.
Hi. So XGBoost is quite popular now. So can you talk a little bit more about why XGBoost outperform comparing to other gradient-based methods in terms of like classification or regression performance?
You mean why does it perform well?
Yeah.
It's because of power of tree-based ensemble. That it's because of the model actually. If you look at the performance, for example, before XGBoost, random forest is another tree-based ensemble method that works well. Gradient boosting is usually more powerful than random forest. Usually it's harder to train and harder to parallelize, but we solved that problem. So yeah.
Okay.
Hi, nice talk. I had a question about the regularization term that you added to the loss.
Yeah.
Have you done any experiments comparing that with other ways to regularize like bagging and so on, which seem to be popular as well?
Actually, we support all the regularization you talk about,
Right.
including bagging, subsampling columns like random forests, and the regularization and explicit regularization. And we find that combining all those, they are kind of orthogonal to each other, and it's good to combine them together.
Yeah, I wonder if you had any results because you called it out in the beginning of the talk, so I was curious to hear if there
There are more results
there.
actually on the paper besides the result I
paper?
show. On
Okay,
this.
awesome. Thanks.
Great talk, by the way. So I have gradient boosted trees are actually quite popular because quite extensible as well for multitask learning, or you can add additional trees. You can learn a base model and then add additional trees for on top of it and so on. I'm wondering if you can comment on the extensibility of XGBoost. Can we do have a base model and learn on top of it, or transfer learning?
Yes.
And so on?
So actually, we support a customized loss function objective so that you can write your own objective function depending on your need, and that's actually many people find it very helpful. Yeah. So it includes tasks like regression ranking, classification, and survival analysis, for example. Yeah.
Hi, thanks. Another question related to the missing value handling. And so you said something about the preferred direction or something like that. Can you say something more about it? And do you make any distinction between missing at random versus missing being informative? Thanks.
The thing is that we do not make distinction between missing at random and missing and other additional informations. What we do is that we directly find the default direction that optimizes the training loss, and that's usually correspond to learning the imputation values for the missing value, and usually that works well. Yeah. Hope that answers your question.
Great talk. I have a question about distributed version of the XGBoost. I was actually previously using the Spark version of XGBoost, and one issue I found is that if one instance died out, or because of out of memory, or the cluster just killed it, right now there isn't really a robust way to recover the entire algorithm. I have to kill everyone and restart. Sometimes they just hang there. Is there any plan to further increase the system fault tolerance for the entire distributed version of the XGBoost?
XGBoost is based on a rabbit abstraction that's designed to be fault tolerant. So in theory, if some of the job dies, it will recover elsewhere, and the entire system will be able to continue in a sense that it is fault tolerant. With respect to your question, I guess there might be some details in how we can configure things. For example, the job restart, job retrial time, and things that we can bring it offline. But yes, it is fault tolerant.
Thank you.
I think we're done. Thank you very much again.
Okay.